All right, thanks for joining us again. We are so happy and delighted to have Matt Gentzkow joining us. Matt has written so many wonderful papers on everything from Facebook to how doctors behave, and I'm really excited to hear his talk today. So thanks so much, Matt, and please, the floor is yours.
All right, well, thank you, everybody. Let's see, can you all see my screen? Work? Great. So it's a real pleasure to get to be with all of you today and be part of this. I think this is such a great institution that you all have created, this summer school. I think it's just fantastic. So it's great to be part of it. I thought I'd take, in the little bit of time we have today, the first part of it to talk at kind of a broad level about text as data and machine learning methods as applied to text. And then in the second half of the time, talk about some specific work that I've done with co-authors looking at the evolution of partisan language and partisan speech. So this first part is going to partly follow a survey article that I wrote with Brian Kelly and Matt Taddy, which you can see in Journal of Economic Literature if you're curious to read more about that. So I think we may have gotten to the point where this seems obvious, but there's a huge amount of text out in the world. I think if you sort of think about what social scientists are trying to do, it is a fundamental constraint that we can only study human behavior that is measured somehow and recorded somehow. There are a lot of different ways that society and human behavior get recorded, including censuses and surveys and administrative government databases and so on. But if you sort of step back and look at it, a huge amount of the way societies and human behavior and interaction are recorded is in the form of text. And as recently as really when I was in grad school, which was long ago, I guess now, but sort of 20 years ago, there was very, very little work in social science that was exploiting that text as a form of data. And that's one of the things with the growth of computing and machine learning and better methods that's really exploded, and I think it's really exciting. So this ought to be something that social science can learn a lot from. And indeed, I think social science is learning a lot from it. This is just like a very short list that we could make much longer. There's work in finance using text from financial filings and reportings, social media, company filings, to do things like predict asset prices. There's work in macro, thinking about policy uncertainty, thinking about forecasting, measuring causal effects of Fed announcements, work in IO, work in political economy, of which the stuff I'll talk about today is some, and also work in media economics, looking at the output of media and the content of media. So there's lots of places where we're doing this, and I think lots more places where we could be. Think about, well, why haven't people always used text as a key data source? And why does using text require doing anything different than we would in some other contexts? I think in this context, talking about machine learning, it's pretty obvious that I think fundamental difference is the dimensionality of the data source. So if you sort of think about measuring the dimensions of various kinds of data, if I have a data set with a bunch of individuals and their income and their age, that's a data set with 2 dimensions. You could think about these, discrete values in some data set that lead to 4 dimensions. Suppose I take some text, which a common example might be a sample of Twitter messages. And the vocabulary of words that could be in those Twitter messages is really tens or even hundreds of thousands of possible character strings that could appear. But suppose we keep things simple and imagine that the vocabulary that people use in Twitter is 1,000 words. Then that sample of messages, if we just encode every possible message flexibly, has about 10 to the 90 dimensions, which is a lot of dimensions. And in the kind of completely flexible representation of that text, that's going to be something that if you sort of try plugging it into any standard statistical approaches is not going to work very well. So text is high dimensional, akin to lots of other things we're talking about here. That makes it a natural place to apply machine learning methods that are designed for high dimensional data. And so it has similar properties to things like genetic data, images, and lots of others. As we'll talk about a little bit, there are some cases in which all the research is really doing is taking off the shelf machine learning methods and applying them to text. And in other cases, there are methods which, whole worlds of methods that are really customized to the case of text. So that maybe seems kind of obvious. The other thing that gets discussed less, I think, is that this high dimensional setting not only means that we need a lot of fancy computers and methods, but also that we really, really need humans as well. And a way to think about that is, in order to make any progress, we actually have to bring a huge amount of prior information about this data to the table, in addition to using good methods. And I think this is in some ways a point that applies much more generally to all of the other kinds of high dimensional data you guys are talking about. Sort of easy to think of it as like, oh, well, we now have these very flexible learning methods, neural nets. We can just take whatever data we have, throw it into the computer, take predictions out. But the reality is that effectively doing that actually requires a huge amount of applying prior knowledges to make decisions and structure what we're doing in ways that are going to be effective. If we think of the completely unstructured version, where we just represent the data as a 10 to the 90th dimensional vector of each possible Twitter message that you could construct from that vocabulary, I would challenge you to find any machine learning method that is going to have any hope of forming good predictions from that data if we just throw it in. So what we're doing in many settings is applying prior information, and text is a case where we have a ton of that. Because fundamentally, language is something that we actually know a lot about, and something that has a lot of very rich structure. And that is rich structure that humans understand, but computers don't, for the most part. We can try to teach them, but we know a lot about it. And so thinking about, every analysis of text that I know of begins with some huge dimension reduction step, where we're going to, before we get to automated dimension reduction, where we're just going to manually reduce the dimensions by saying, let's represent the text as a vector of counts, or let's represent the text as a vector of skipgrams, or let's represent the text as some other much lower dimensional object using our priors. So the other thing, which is a general point, which I'm sure comes up often in the discussions you're having, because I think it's been really essential in the interface between statistics and machine learning with economics, is the question of, to what extent is what we're trying to do prediction, or to what extent is what we're trying to do causal inference. A lot of the methods in general from statistics and computer science grew up in contexts where the main goal is prediction. There's some outcome Y, we have some high dimensional data X, and the goal is to produce a prediction, some function of X that will generate a prediction of Y that has nice properties. Most empirical work in economics, we know, is not about that, but about causal inference. And I think this tension is particularly salient in the text context, where we can do a lot of predicting things from text, but figuring out how to use text effectively in causal research adds another layer of challenge. So I think of two ways you could think of why causal inference is different than prediction. One that in some sense people often talk about is, well, and I think sometimes statisticians who are kind of impatient with economists' obsession with causal inference will sometimes talk about this as like, well, economists are obsessed with the idea that F is some true model of the world that must have some structural interpretation. And so causal inference is about trying to assign meaning to that function, to say that like some coefficient in some lasso model has to have some interpretation, whereas statistics has a kind of more agnostic point of view that none of these models are right, and we're just trying to solve a prediction problem. So you could think of it that way, that we care about the interpretation of that function. Or I think another way to think about it, which I find helpful, is just F is a description of a DGP, is a description of the joint distribution of X and Y hat, conditional expectation of Y hat. And it's a joint distribution that is very specific. It's the one that we happen to observe. And causal questions are, in a sense, questions about different DGPs than that. For example, what would happen if we varied education in a world where people's skill and other variables were held constant? And that's a DGP that we never get to observe. So causal questions are, in a sense, fundamentally about extrapolating from a joint distribution that we observe to a joint distribution that we don't observe. And no amount of fanciness in the methods with which we estimate the joint distribution of X and Y is going to solve that problem. We have to apply, again, prior knowledge and careful research designs and experiments and so on. Okay. So we can think of examples of both of these in the context of text. There's a lot of good research where the goal is simply prediction. Kind of classic early application of text analysis was spam filters trying to tell which emails are spam or not spam. That's a prediction problem. Trying to figure out who wrote an article. Another even earlier famous application of statistics to text, this Bosteller and Wallace is a kind of famous seminal article trying to figure out for an unknown text, in this case, text that might have been in the Federalist Papers that might have been written by Madison or might have been written by Hamilton. We don't know who. That's a prediction problem. There's a lot of trying to back out variables that we don't observe from text data or search data. Predicting flu outbreaks was a classic early example, predicting COVID, predicting unemployment from text. Trying to use financial news to predict, forecast asset prices or to build trading models or to run hedge funds would fall in that category. And then there's a bunch of examples in current work of cases where the questions are causal. So that would include things like, for example, Seth Stevens-Davidowitz's great job market paper that used Google searches to estimate racial animus at the local level and study the causal effect of that then on votes for Obama in the first Obama election, looking at using text to measure political slant of news outlets and then studying supply and demand forces that drive that, looking not at forecasting asset prices, but at the causal effect of financial news on asset prices, which is very different. Work in finance doing that, looking at this great recent paper by Ash et al., looking at the text of judicial rulings to figure out what was a causal effect of sending a bunch of judges to courses in law and economics on the way the law was shaped and so on. So for the purposes of this, I want to think about almost everything we're doing, almost everything that's being done in all of these contexts can be kind of thought of through this template. We start with some text. We don't actually do anything with that directly. We first, largely using prior information, represent that text as some numerical array, X. We use some methods, some statistical methods to map X to a predicted value Y hat of the thing, an outcome or a characteristic we're interested in Y. And then we take that Y hat and do something with it. It may be that if we're doing prediction, that's the end of the exercise. Maybe if we're doing causal analysis, Y hat is a measure of local racial animus. And the point is to then take that and put that on the right-hand side of a regression to do some causal analysis. Okay, so let me talk just a little bit about those steps. Okay, so how does this representation happen? There are a few steps in the way that usually happens. So first, we can, in most contexts, think of the text that we have as a collection of documents. Those could be email messages, speeches, columns, tweets, and so on. And typically, we're going to structure the data, not always, but often we're going to structure the data so the rows of Y and X correspond to those documents. Then in a large share of contexts, and particularly a large share of existing applications of text to social science, we're going to represent each of those documents as a vector of counts of something, counts of words, counts of phrases, counts of other text features that might appear. And notice that that's like doing incredible violence to the data. It's basically at like step one, we're going to throw out a huge amount of the richness of what makes text text. But I think the interesting fact is that in practice, that tends to work remarkably well in many contexts. So if we do that, if we said, let's go from raw Twitter data to a matrix of counts of each word in those Twitter data, we now have 1,000 dimensions instead of 10 to the 90th, which is pretty decent improvement. This is sometimes called bag of words representation of text, where we start with a document and what we produce is a vector of counts, the number of times each word in some vocabulary appears. We can do that not only with words, but also with phrases, 2-word phrases, 3-word phrases, 4-word phrases. That gets us a little closer to incorporating the richness, the semantic richness of the text. So it seems crude, you'd think it would be terrible. It actually works pretty well in practice. And then again, coming to this point about priors, there are actually, in any typical case, a huge number of other manual steps and choices that people are making to further reduce the data, to isolate the information that seems most interesting. So that can include dropping uncommon words, dropping very common words like that do not carry a lot of semantic information, stemming words, dropping HTML tags or numbers or punctuation or other things. So, okay. So we take raw text through some combination of those choices, we reduce it to an array. And then the question is, how do we do this step of from those arrays forming predictors y hat of y? And that's basically where all of the machine learning comes in for the most part. And I'll come back again. There are interesting methods that go beyond this kind of counting approach, which I'll circle back to at the end. But for now, just to kind of think about the space of methods as they apply to text. So we have X. X has n rows and p columns. So n is something like the number of documents. P is something like the number of different things that we're counting. Like if it's words, the size of the vocabulary. And this fits into the machine learning world because P is often of similar order to N or larger than N. So we can't just regress Y on X in the simplest way. So we're trying to form Y hat. What is Y in these contexts? So it's useful to note, actually, there's kind of two classes of problems. One is where Y, the thing we're trying to learn, is itself some characteristic or function or feature of the text. So is an email spam or is an email not spam? Who is the author? Is this news article slanted in favor of Republicans or slanted in favor of Democrats, and so on? So there, we're trying to learn some specific characteristic of the text itself. And then there are a lot of other contexts where the predictive step is trying to forecast something outside of the text based on the text itself. So forecasting investor sentiment in financial markets, or flu cases, or COVID cases, or racial animus, or city level corruption, or the unemployment rate, inflation, so on. These are all cases where the Y is going to be something which is not about the text itself, is going to be some real world variable that we want to relate to it. I don't know why. Okay, so the methods for doing that can be divided, if you look across the literature, can be divided basically into 3 cases. The first, which is not very exciting for a summer institute in machine learning, is what we call in this paper dictionary-based methods, which is essentially, let's just assume that we know what F is from the beginning and not use any machine learning to try to learn it. And that sounds awfully simple, but it actually accounts for a large majority of applications of text in social science so far. And you might think, what terrible evidence of the backwardness of social science. But I actually think, there's some of that, but there's also a lot of context in which actually we're going to beat the computer with our prior information, and we would be better off using that directly. And so if the goal is really to classify like how many news articles mention Donald Trump, I don't really need to train a model to forecast which words predict that a news article is mentioning Donald Trump. I can just define my function f to be, does the news article contain the word Donald Trump, and I'm done. Lots of other things look like that. There are sentiment analysis that use predefined dictionaries of positive words and negative words, or happy words and sad words, and so on, all fall into that category. This influential work by Baker, Bloom, and Davis on economic policy uncertainty is an example. If you look at their original paper, how do they define economic policy uncertainty? It is just defined to be the number of news articles that contain a predefined set of words that have something to do with economics, something to do with policy, and something to do with uncertainty. So that's a dictionary method. Second category, which gets more interesting, is what we would call supervised methods, where we have a training set and a test set, basically. So we observe the true value of y for some subset of cases, and the goal is to predict y hat for the remaining cases. And you can think about all of methods you know and love to solve problems of that form. Spam filtering is an example of that. And then the final category is unsupervised methods, which hopefully you all are also learning about and also know and love, where y is not observed for any of the documents. So we have to infer it from all of them. Obviously, if we don't make any assumptions, we're not going to be able to do that. But if we make assumptions about the structure of what y is and how it's related to x, then that structure may be enough to allow us to infer y, even though it's never observed. And so things like principal components analysis, factor analysis are an example of that. Topic models in the text context are an example of that, which are basically factor models rejiggered for multinomial data news. Okay, so yeah, I'll skip over this detail, but we talked about dictionary methods. Supervised methods you can think of in two further flavors: regression-based methods, where we're doing something that looks like regressing y on x in the training set, and what we call in this paper generative models, or you could think of as more structural approaches, where we are flipping things around and writing down a model for x as a function of y. So if you were, imagine you were trying to figure out the ideology of a speaker based on their speech, as we'll talk about. One thing you could do is just regress ideology on the count of a bunch of words that they said, and that would be a regression type method. Another thing you could do is write down a model. Why is the model flipped? The model's flipped because we don't actually think that the causal relationship goes from x to y. It is not the case that you say a bunch of stuff and then whatever you say causes you to have an ideology. It is instead that you have an ideology and your ideology causes you to say certain things. And so when we write down models, even though the predictive step has y on the left-hand side, the model is going to have y on the right-hand side. And so we're going to model that relationship, model x explicitly as a function of y, and then use it to derive an estimator. So lots of different methods fall into these cases. The regression methods are going to look like regression methods in all kinds of other contexts: penalized regression like lasso, regression trees and forests and variants of those, support vector machines, neural nets. These are all essentially forms of regression. Examples of generative models in the text context include naive Bayes, which is like an early generative model for text, partial least squares, multinomial inverse regression from some work that Matt Taddy has done, and lots of others. And then unsupervised methods. There is no regression method for the unsupervised problem, because if you tried to run the regression would have 0 observations. So you can't do that. So the only unsupervised methods are going to involve generative models. And there are lots of examples of those. So principal components we said is one, clustering algorithms like k-means clustering or another, topic models or a third, and there are many more. And then the final thing, that this is, I think, the most important place where this discussion of methods that all operate on data where the text is represented as counts of things, where that is limited, that still describes 95% of applications of text in social science, or 90%, or it depends whether you look at just most recent papers or over some span. But the most important thing that omits is embedding methods, which, if you look at the literature on NLP, kind of have become an incredibly important part of the toolbox. Think about like computational linguistics is the part of the machine learning space where people care most about the actual semantic features of the text and understanding, if you're trying to like design an Alexa that can sit in your house and like talk to you, having a bag of words representation of text is not going to work very well. You would have a very poor Alexa if Alexa was just like a multinomial IID word generator. So there's a whole part of the world where we actually do need to think a lot about the structure of text, and these word embeddings or vector semantics are kind of the essential tool from the last 10 or so years in that literature. So there's a bunch of these methods. The basic idea is, instead of doing dimension reduction to counts, we're going to do dimension reduction to some lower dimensional vector space, which is arbitrary and which is going to be learned to capture as much of the relationships between words as possible. And so there are a number of different ways. You're still going to have to take a manual step at the beginning to figure out how to represent your gazillion dimensional data as a vector of as a matrix, an array of numbers. And there are a few ways to do that for these embedding methods. One common one is what's called co-occurrence data or skipgram data, where we want to represent in the matrix which words appear close to other words. I'm not going to actually use where exactly next to them they occur. We're just going to define a window and say the word jam co-occurs with the word apricot in this document if jam is within 3 words or 5 words or 7 words of apricot. And so for each word in the vocabulary, we can then ask, how many times does every other word co-occur? And so in these examples, the word apricot co-occurs once with pinch here, once with sugar over here, never occurs next to the word computer, and so on. And so this is encoding a lot more information than word counts, and it's encoding more information than something like 2-word phrase counts. And so roughly speaking, the way to think about word2vec and other vector methods is we want to assign each word a low dimensional vector such that we can predict this matrix well from just knowing the vectors. So if I tell you the vector associated with this word, and I tell you the vector associated with each of these words, you're going to do a good job at predicting which occur close to each other. And so that step is often like a neural net step, where we say, given some set of vectors, we'll use a neural net to figure out which words are likely to, if I have a vector which is 0.3, 0.4, 0, 0, 0.1, which things are likely to co-occur with that, I can learn with a neural net. And then I'm going to try to define those dimensions, define the vector, search over possible vector representations to find the ones that work the best. The key thing that's going to do is it's going to assign similar vectors to words which tend to occur in similar contexts. And what that means in practice is that words that have similar vectors are going to end up being semantically similar in their meaning. They might not look at all like each other, right? In terms of the characters in the words, they might be totally different, but they're going to tend to words that have similar meaning or similar function, like apricot and pineapple, are going to appear in a similar place. And that also, the kind of awesome, cool thing about this is it also means that the structure of that vector space, like into what direction is one word from another, is going to encode a whole lot of meaning. So there are lots of just great examples of once you fit these models and go look at them, there are all kinds of neat things. So you can sort of project them down into different two-dimensional spaces. Here is a bunch of words projected down into 2 dimensions, where you realize that there's a direction through this space which the model has just learned endogenously, which corresponds to gender. So words that are a female version of one word are always oriented in the same direction relative to words that are the male version of that word. Didn't tell the model anything about that, but that arises endogenously. Or relationships like short, shorter, shortest have a consistent directionality in that vector space as well. And you can also do cool things like look at how these embeddings change over time and how the location, like who are the neighbors of a given word in different points in time. So how the word gay has changed in its meaning from the 1900s to the 1990s. Broadcast, if you fit the vector model in 1850, is all about farming. Broadcast, if you fit the vector model more recently, is all about radio and TV. Okay. So I will stop there and flip over to partisan speech, unless anybody has any questions. Okay, great. Now for this part, you have to ask some questions. When I'm just like rambling on about generalities, I don't mind, but if I'm now going to really talk about some research, so please interrupt me and ask some questions as we go along. So I want to talk now about partisan speech, and in particular, I'm going to focus on this 2019 paper with Jesse Shapiro and Matt Taddy, which is called Measuring Group Differences in High-Dimensional Choices. And so that paper, as you can tell from the title, it sort of has, there's 2 ways to think about it. One is the paper where we're trying to study the partisanship of speech over time. And the other is it's a paper where we're trying to think about a generic problem, which is how do you use machine learning type methods to learn the difference in the choices between 2 agents, basically. So that could be how different are the choices of men and women, or Republicans and Democrats, or how different are the residential choices of people from different groups. It could also be how different are the choices in one year from the choices in another year, which is what we're going to be doing here. And so all of the issues that come up in this paper are really generic issues that are going to apply whenever we're trying to apply these sorts of methods to looking at differences between groups. And I think that like the big idea, not big, but like the main idea in some sense is just we're going to, if we are looking at, we don't know y, so we're looking at y hat, and we're going to be looking at the difference in y hat between one group and another group. We have to be particularly careful about whether those differences are reflecting differences in the underlying y's, or reflecting systematic differences in the errors y hat minus y. And that's really, in a sense, all that's going on here. Okay, so if you haven't noticed, there's a lot of partisan language out in the world. People on different sides of the ideological divide in this country, in other countries, speak systematically different languages. They live, in a sense, in different worlds as defined by the words that they're saying. Some people talk about freedom fighters, some people talk about terrorists, some people talk about illegal aliens, some people talk about undocumented workers, and so on. This kind of language doesn't arise just by accident. There's a lot of evidence and narrative to suggest that it's largely chosen strategically in the political space. So a lot of the phrases and language that we use didn't arise just because people decided to start saying those things. We know they arose because strategic actors intentionally chose those phrases to achieve some kind of persuasive effect. So these memos are famous memos from a consultant called Frank Luntz from 2009, where he basically produced a whole handbook of 4 Republican candidates running in that year. What are the words that we should use and what are the words that we should not use? And these kinds of talking point type memos are obviously familiar. An example from that, going a little ways back, once upon a time when George W. Bush was president, there was a big debate about whether we should have private accounts for Social Security, i.e. we should have the Social Security program administered by private firms rather than the government. And Luntz did a big study and sent this memo to a bunch of Republicans running for Congress saying, we've tested this, and if you're going to talk about this, you should not talk about privatizing Social Security, which happens to be what everybody had said up until then. This is a debate about whether we should privatize Social Security. Turns out people don't like that. It makes them nervous, or it makes them think about Russia or bad other things. And so instead, you should talk about private accounts. You should not talk about private accounts, but talk about personal accounts. People like that. That sounds better. We're going to personalize Social Security. And if we do a bunch of focus groups, we see people are much happier to personalize their Social Security than to privatize it. Okay. Turns out that if you go look at what politicians said in that Congress following that election that the memo was released for, they really follow this advice. So Democrats overwhelmingly talk about privatization and private account, whereas Republicans got the memo and only say personal account. We don't know what happened to this 5 Republicans who said private account. They maybe were punished in some way, but so this is clearly explicit strategic behavior. And what it means is, if you were trying to guess whether some congressperson was a Republican or a Democrat, knowing which of those phrases they chose would have a huge amount of information. So a way to think about the sense in which this is partisan language is language which is very diagnostic of somebody's party. And we'll circle back at the end to why you might care about this. It's like a fair question. Who cares how politicians in Congress talk? Good question. I don't know. One thing which is a reason to care is this language, which often begins by strategic choices by politicians, then filters out into the wider society. So it filters out into media. If you went and looked in that year at news headlines about this debate in Congress, you would find left-leaning outlets like the Washington Post talking about private accounts, and you would find right-leaning outlets like the Washington Times on the same day reporting on the same thing, using the phrase personal accounts. And from news media, it filters into all of the rest of our speech and the way we think about the world. Okay. So none of that is new to this paper. We've known about partisan speech for a while. What this paper is trying to do is ask, well, how new is this phenomenon? How is this thing where there's these phrases and all of the Republicans are using one of them and all of the Democrats are using one of them? Is that something that's always been part of American politics? Is it something that's gradually evolved over time? Is it something that is actually very new? If so, when did it start? Those are the kind of questions we'd like to ask here. And you can see those then become questions about group differences and high dimensional choices, because we want to ask, how different are the language choices of Republicans and Democrats and in early years versus later years? So we're going to try to do that in this paper. The paper really started with getting access to a really great source of complete text data for the US Congress going all the way back to 1873. So there's a law in the US that says everything that's said in Congress has to be written down. And so we have digital copies now of the congressional record. It takes some work to parse it and get it into a form that you can use it. I'm not going to talk a lot about that. But then the challenge is, again, speech is high dimensional. If I just wanted to look at how has the use of the phrase private accounts and personal accounts evolved over time, that would be easy. I don't need any, there's no statistical problem there. But once I want to incorporate all of the phrases and let the model learn on its own which are those phrases that might be diagnostic of party, we have this high dimensional choice problem. So one thing we're going to show is if you do this in what might seem like a sensible way, and in a way that some previous published work in the literature had done it, you're going to get the answer very wrong. And you're going to get very wrong because of some finite sample bias that arises in this problem, which is very systematic and severe. That's one challenge that we show that you need to solve. The other challenge is just computation is difficult when you're working with such high dimensional choices. And so we also suggest some methods to address that. And so basically the estimator we're going to propose in this paper is a generative model of text, i.e. structural estimation, using penalization and shrinking to address the finite sample bias, and also using some tricks to solve the computational problem. Okay. So the data come from the congressional record. We're going to parse these things, figure out who's speaking, map those speakers to who they actually are and their party. We're going to remove a bunch of procedural language that tends to gum things up in Congress. And here we're going to focus everything on counts of two-word phrases called bigrams. So two-word phrases turn out to have a lot more information about partisanship than one word, kind of bag of words that might be one starting point. So if you thought about, the word private and the word personal by themselves are not super partisan, but private account and personal account are very partisan. So this is a case where you get a whole lot more information if you use a little bit of the relationship information by using two-word phrases rather than one. And you could also use 3 or 4 or 5. You could also train word embeddings and use even richer information in that way. You can go, this data is all publicly available, so you can go work with it if you want. We're then going to follow lots of the machine learning literature in describing the model of how text is produced in this incredibly stylized way as basically an IID multinomial that, as we said, is a terrible description of how language is actually produced and would not work well if you were trying to program Siri on your phone, but for predictive purposes and for this kind of inference actually works remarkably well. So there are a bunch of speakers, like different Congress people. There's a vocabulary of possible phrases. There are a number of different sessions of Congress. And so we're going to collapse the data into counts of how many times speaker I said phrase J in session T, and let bold CIT be the vector of those for speaker I in session T. Each speaker has a party affiliation. Each speaker might also have some X's, observable characteristics. Let M denote the total number of things that speaker I said in session T. And then we'll model C as a multinomial with M draws from a probability distribution Q. So this bold Q is a vector with one element for each phrase in the vocabulary, which is the probability that somebody of this party in this session with these characteristics says that phrase. So this Qs are kind of the key element in the model. They're like choice probabilities by party. You can forget about the X's, but really it's like in each year by party, what are the choice probabilities? And then partisanship is going to end up meaning just how far apart in some metric is the vector of Qs for Republicans and the vector of Qs for Democrats. That's really, at the end of the day, what we're going to be doing here. So we have to learn the Qs and then look at how far apart they are. Right? How different are the choices of R&D at each T? How different are those vectors? And so you could think about a bunch of different metrics. We actually show in the appendix, you could just use the Euclidean distance between these vectors, and you would get back a pretty similar result. Things would be a lot noisier, but actually that would work fine. You could think about mutual information or other distance metrics. We're going to measure partisanship by diagnosticity, which is a particular metric, which is basically going to say, how much could I learn about which party you're in based on what you say if I knew the true Qs? If I knew these true Qs and I see you say something, how diagnostic is it of your party? Arushi, you had a question.
Yeah, thanks. I was just wondering, how did you decide the parametric assumption on the distribution from which the counts are being drawn? And I mean, you sort of mentioned that it might not be very important, but I was wondering if what are the advantages of using this approach rather than being completely, say, non-parametric about it?
Yeah, great question. So there's a couple of ways to answer it. So one is, I mean, we are, in a sense, being completely, well, there's two levels of parametric structure here. One is making this multinomial, and the other is the particular way that we might parameterize these Qs in terms of X's. Suppose we forget about the X's and just think of these as arbitrary vectors, then we're in a sense being non-parametric here, conditional on modeling speech as IID draws. So this is like a very flexible model once you think of speech as every word is drawn IID. Where it's dramatically not flexible is that assumption. And I think that basically we're building here on just lots and lots of prior literature that has built on models of that form, and also, you know, maybe somewhat informally, but I think a lot of our experience and experience in the literature that shows that in these kinds of contexts, the gain to trying to model finer characteristics of the dependence of speech is not all that big. And so this kind of works well. You can think about it, you know, again, if this was word counts being IID, that would be one assumption. What we're assuming is each 2-word phrase is IID. That's incorporating some of the dependence among words. And a way to think about it is, if you play with this, you would see the gain from going to 1 word to 2 words is really big.
Right.
The gain from going to 2 words to 3 words is not that big. The gain from 3 to 4 gets really small. And so that sort of gives you a sense that if you're trying to think about partisanship, there's diminishing returns. But it remains open. Some people have been working on things like applying those word embedding methods that I was talking about. And I think you could do, it's like an open and interesting question. What are the directions of richer modeling that give you big gains? Lindsay.
I had a very similar question. When you introduced the examples, there were very much partisan word examples rather than partisan speech. And so when you think about measuring speech, which potentially is where some of these machine learning models that are not bag of words would come in, where maybe you could get you could pick up some interesting trends, is going. Do you have any sense of, like, given that you've played around with this, is there increasing gain from getting more complicated, or because a lot of the phrases that people make strategic decisions about are actually words, there's less gain from doing that?
Yeah, I think what I know is certain directions in which you can move toward richer representations produce relatively small gains in this predictive problem as it's specified here. But on the other hand, we know to a human doing this, the actual, like, listening to the entire paragraph of what somebody said has a huge amount of information which is lost here, and would in particular have information about somebody's party. So, you know, you could imagine a world where people don't use coded partisan phrases and partisan language. They just make arguments, and it's really the form of the argument you're making and the structure of what you're saying. But what we're going to end up isolating here is this much more choice of phrases, choices of language. Yeah.
I was thinking back to something you mentioned before, which is understanding the kind of y minus y hat, so the errors we make. So I feel like you could, if I understand this correctly, you could frame this as saying you want to predict party affiliation from speech. Now, in a way, I feel like we're not really predicting party affiliation. We're probably predicting partisan speech, because don't have to be the same thing. So if you think of predicting party affiliation but making a mistake, it could also be because there's a Democrat who specifically wants to appeal to, you know, a Republican base and therefore uses Republican language. So I was wondering where that plays a role here, whether you could also use this approach to basically say something about, you know, the label is actually not directly measured. The label is really, does somebody talk like Republican or Democrat? And it may actually be interesting structure in the fact that we can now uncover this label, which wasn't available before, and even talk about, you know, the dynamic of somebody in a swing state talking like a Republican despite being a Democrat.
Yeah, that's a great question. A couple of things. So one, just in a simple sense, something you can do here is say, instead of using binary party affiliation, use a continuous measure of somebody's ideology. And, use that as what you're trying to predict. So one direction you can move is some of the ways in which Democrats might be doing different things are measurable. So you could do that. But the other idea, which is fit a model to predict the binary thing and then look at who has big residuals on one side or the other and try to understand that, is actually incredibly important in this literature. And there's a lot of stuff that has that flavor. Some of the work that's training models on Congress and then going to look at news text, you can sort of think of in some sense in that way. It's like, what is the score that you get based on this model, based on what you actually said? Do you end up sounding more like a Democrat or sounding more like a Republican? Has exactly that flavor of using the residual variation. And people do things like fit the binary model and then go look at Congress people and ask which ones on their residuals end up talking more like a Republican or less like a Republican. You could think of using that as a continuous ideology measure, and people have done things like that. So absolutely. Okay, so let me just show you a little bit more of this. Can at least kind of get to the main result. Okay, so suppose I want to use diagnosticity as a metric on the difference between these vectors. In other words, I want to say how much, given the way people speak in a given year, in a given session, can I infer about your party based on the choice of words? So to build that up, let's start by noting that if I have a neutral 50-50 prior on what your party is, and I hear you say one phrase, and the one phrase that you say happens to be phrase J, then my posterior on the probability that you're a Republican rather than a Democrat is going to be given by rho, which is just the probability you would have said that if you were a Republican divided by the total probability that you would have said that. That just comes from Bayes' rule. And then what we're going to focus on to define our measure is a slightly fancy transformation of these, which is just the expectation of this posterior from the point of view of an observer who doesn't yet know what will be the party of the person talking to them or their choice of phrases. So the posterior that a neutral observer expects to assign to the speaker's true party is given by pi. So if the person is actually a Republican, that happens with probability 1/2, then they'll draw from Q, and my posterior on the true party will be rho. If they happen to be a Democrat, they'll draw from QD, and my posterior on their true party, which is that they're a Democrat, will be 1 minus rho. And so pi is, you can think of as a measure of basically how well I can predict someone's party based on hearing them say one thing. And then our main measure is going to be this averaged overall of the speakers in a given session. So across all of the speakers in a given session, what is the average of that? So how would we estimate this? The kind of starting point is going to be, well, there's a really obvious estimator, which is the maximum likelihood estimator of this model, in which we would just plug in Q hats and rho hats. So we estimate Q hat based on the empirical share of the phrases Republicans said that were J or that Democrats said were J. We could plug those into rho. We could plug that in here and get an MLE estimator. So this is going to be just like a direct plug-in estimator of pi hat. And that might be a pretty sensible thing to do. Previous research has taken versions of that approach. Here's what you would get if you did that. So this would be the answer to the question, what's happened to partisanship over time? And so you would learn, well, it used to be really high. In the 19th century, early 20th century, speech was very, very partisan. It fell steadily up until about 1970, and then it's ticked back up a little bit recently, but nowhere near the levels that it was before. So we did this early on in this project. We spent a bunch of time staring at this picture and thinking about how interesting it was and telling stories about what was going on in 1910. And then at some point we had a good idea, I think, which I'm sure must have been Matt or Jesse's idea, which was just to like make sure we're not screwing something up. Let's construct a data set where we randomly assign people's parties, just randomly reshuffle all the party labels in the data and recompute this series. And if you do that, you get this. So this is exactly the same estimator based on a data set where all of the party labels have been randomly reassigned. So in that case, you know the truth is 0.5 everywhere. That is the true value of pi. And so this tells you something is not going so well here. And in particular, there is this big finite sample bias that this naive estimator has. Now, why is that going on? The intuition is actually pretty simple, which is that model is going to be wildly overfit. They're going to be in a large vocabulary with a relatively small amount of speech. There are going to be a ton of phrases that are said mostly by Republicans or mostly by Democrats purely by chance. And this plugin estimator is going to take any phrase that was almost only said by Republicans and assign that a really high value of Q, and any phrase that was only said by Democrats a really low value of Q. And it's going to, if you just took those as the truth, you would have, you would think that there was a huge amount of predictability. This is the actual published series, this pink line from the previous paper doing essentially the same thing we're trying to do here, which was this pink line, which you'll notice looks a fair bit like this pink line. And this gray dashed line is what you get if you do the random reshuffling in their data, which suggests that this, which was a big part of the conclusion of that paper, that there was this high partisanship in the past, is really an artifact of this small sample bias. So what do you do about that? And then I'll show you the main result here. And then I think we're probably out of time. We propose two things in the paper. So one is a simple kind of model-free thing you can do, which is a leave-out estimator, where you replace these row hats that we had before based on the full data set with leave-out row hats based on every observation other than observation I, and then plug those in place of the real row hats. Now, I won't now try to explain exactly the intuition for how that works. We walk through it carefully in the paper, but basically all of the bias here is coming from the fact that if a Republican says a phrase and no one else said it, we're measuring the partisanship of what they said based on their own speech and producing this estimate. And so this leave out approach gets rid of that. And if you do that, you get something that looks like this. The random series is at 0.5, which is what it should be. And we have a very different picture of what happened to partisanship of speech in the US, which is that it actually was pretty flat and pretty low for a long time and changed really dramatically around 1990. The other approach is this more ML kind of approach, where we're going to use this explicit generative model, basically a logit model, logit type model of speech with a lasso penalty, and some tricks based on some of Matt's earlier work to address the computation. That's the shrinkage here is going to control that overfitting and control that small sample bias. And so here's the main result of the paper. When you do that, you get an even more dramatic sense in which partisan language in Congress really is a new phenomenon. It actually was quite low and quite constant over a long period of time, and has exploded dramatically. So in the paper, you can see a number of things you might be wondering. One is, how do you think about the magnitude of this increase? So we have some ways in the paper to think about how your expected posterior would look if, instead of seeing one phrase, which is what the main measure is, if you saw 1 minute of speech, 2 minutes of speech. And so the main estimate corresponds to a chance of guessing somebody's party correctly of about 75% if you hear them speak for 1 minute, compared to 55% or so in earlier periods. And then we also talk a bunch about what do we think happened in 1990. And I think this was actually a really consequential, this series basically ticks up in the year that the Republicans took over Congress under Newt Gingrich and the Congress contract with America. And it was an election which was all about language in a lot of ways. So you can see the paper for that story. Thank you all.
Thanks so much, Matt. That was fantastic and super interesting. And I know there are probably a lot of questions, some of which I am curious to ask. The way we set it up is we had a 15-minute break planned just because people have been in front of the screen for a while now. If that's okay with you, Matt, we'll just kind of let people, meditate for a little bit, get some coffee, whatever the right next step is for you, and then come back at 4:15 and go until